So I based today's lecture around, as a demonstration around the second homework problem that we've had. And I think it'll be a nice chance and edifying chance to see how I work a problem, even if you already had a chance to solve this. So I want to come back for starters to that little template that I shared earlier. And that indeed is our first handout. So I wanted to just run through it, and then we're going to follow that as sort of a method for our current work today. Can you see my screen okay? Can you read that on your computer?
Yes.
Great. All right. So what I had outlined before is basically we're going to start by trying to figure out a molecular formula, degrees of unsaturation if we aren't given it, or if we're given it, we're basically given a high-res mass spec. We're still going to inspect various spectra. We're going to try, if there's mass spectrometric data, to identify any special elements present that might stand out, like chlorine or bromine from the mass spec, or even sulfur or silicon. Obviously, we're going to be looking at the IR for things like carbonyl groups and other key stretching frequencies. We'll also be looking at the C13 NMR in depth and trying to orient ourselves. Usually what I like to do and what we're going to do is to sort of make a scorecard. So we're going to look at the IR, note any carbonyl groups. Then we'll go sort of mechanically in the next few steps. We'll go through the proton NMR, letter all the resonances, and inspect the spectrum. And it's important to really engage your mind at this part, because there will be interesting features that you'll see, and I'll comment on them in just a moment. We'll look at the C13 NMR, number the resonances, again, inspect the spectrum. Are there interesting chemical shifts? We saw a problem before where we had a carbon, or maybe it was the current homework set, where we had a carbon at 106 parts per million that didn't seem to be an aromatic carbon, and trying to sort of say, hey, what's up with that carbon? We'll assign our quats, our methylenes, our methynes, and our methyl groups. And then the last part of what I'll consider to be sort of still mechanical is we'll go through the HMQC and correlate the C numbers with the hydrogen letters. Particularly useful if we have stereocenters and have diastereotopic protons. At that point, we're going to use COSY to build up the fragments. If we have a lot of severe overlap, we may use additional techniques like TOXY. Now, HMBC is incredibly important for putting the pieces together. In one of the problems that we're not talking about in today's class, most of the skeleton in this monoterpene 10 carbon molecule can be gotten from the HMBC. One set of cross peaks off an isolated methyl buys you connectivity of 5 carbons, and then another set of cross peaks off a different isolated methyl buys you at least 3 more. In other words, you're able to build up 8 of the 10 or 7 of the 10, 8 of the 10 carbons without any other data. So the HMBC can be very powerful. It's a sea of data. It is overwhelming. The isolated pieces are the most valuable. Methyl singlets are incredibly useful. So in other words, isolated methyl groups. In some of the problems in the homework, although not this one, isolated methylenes can serve in a pinch. Basically, methyls are great because with 3 hydrogens pointing in all directions, you get cross peaks with all the J2CHs and all the JC3H couplings showing up. Carbonyls are useful. Occasionally other quats, although it can be overwhelming. I'll also point out one thing in this spectrum, if I have a chance, to show you one point of confusion on this problem number 2. And as I remind you here, pay attention to other clues like chemical shifts. Now, in the case of severe overlap, TOXI may help you where you just can't walk through the cozy. We're going to, in one of the next lectures, I think it may even be Wednesdays, introduce HMQC TOXI, which is an incredibly valuable technique for dealing with severe overlap. HSQC and HMQC are essentially the same technique, and in some cases you will hear of HSQC TOXI. In some cases you'll hear of HSQC instead of HMQC, and you can think they have differences in pulse sequence, slight differences in what they detect, but nothing significant. Finally, once we work out the skeleton of the molecule, we're going to use NOEs and coupling constants to assign stereochemistry. Models are fantastically helpful. Being able to draw a good conformational drawing is good. Being able to build a molecular model is good as well. I've given on that page I showed you before, I've given when we had our inadequate lecture, I showed you, I've given you some common fragments, and I'm going to illustrate some of those ideas and axial relations today. Occasionally, NOEs can also be helpful for building up the skeleton if you haven't done that as of yet. So that's where I want to stop with this little introduction. Any questions at this point about that? All right, well, I want to start. I always like to keep a scorecard. And so the scorecard that I have here for our molecule for this second problem, I gave you the formula. It's C15H18O3. So that makes it a little bit easy. It's got 7 degrees of unsaturation. And I'm not showing all of this. I hope you've already had a chance to look at the spectra and wrestle with the problem, if not completely solve it. So the IR is interesting. The IR caught my attention on this molecule. We have a peak at 1783, and that's sort of outside the typical carbonyl range for just a plain old, like an ester would normally be somewhere around 1735 to 1750. A ketone would be somewhere around 1715. So that's interesting. That caught my attention. It's consistent with a strained ring or an electron withdrawing group on a carbonyl, but not an acid chloride or an acid anhydride. But we saw some examples where maybe you had an enol ether on there. We also have another carbonyl peak, or at least what looks like a carbonyl peak. So I'm going to write sort of question mark gamma lactone here. We also have a peak at about 1660. 1660 is interesting. That would be normally in the region where you might have a lot of donation into a carbonyl like an amide, but we don't have an amide in this molecule. So it's probably a conjugated carbonyl. We also have a peak at 1629. Could be some sort of conjugated carbonyl, could be some sort of alkene. But again, hard to tell. And it's a reasonably strong peak, which is unusual for an alkene. Conjugation makes it stronger. So I want to take a look. I want to take a look at the spectrum now and sort of inspect our way through it. And what I've done is I've pre-digested the sort of lower level thinking on this problem because I wanted to do what was expedient to get us started here and allow things to work nicely in the time slot. So I'm going to share my screen and share my own personal analysis of this problem. So I went through the proton spectrum and I measured all of my integrals. At that time, I think I was using a ruler in millimeters. These days, I really like my grids, and I just measure grid with the grid to the nearest tenth. So it looks like we have a couple of protons that might be on some sort of alkene, maybe with an electron withdrawing group. We've got a very interesting one over here at 4.7 parts per million. And this is interesting also in its pattern. I didn't give you the expansion on this, but it's clearly got a big coupling for a doublet. It looks like a doublet of doublets with a small coupling, but if you look at the peaks, there's kind of a shoulder on each of these peaks. We're going to see later on, and the shoulder sort of extends out, that it's a doublet of quartets, and it's got a reasonable size J and then a small J that's just right on the edge of what you can pick up. It's right about 1.3 hertz. We've got this very nice doublet of quartets over here at 2.4 parts per million. This methyl peak is really interesting. It's 3 hydrogens. It's at about 2.1 ppm, 2.07 ppm. It's a doublet, and you can see it's a doublet with a J equals 1.2 hertz. So that's not any methyl group that's next to a CH. That's some sort of allylic coupling. That's some sort of allylic methyl. Normally for 2.0, I might say maybe it's alpha to a carbonyl. But if it were alpha to a carbonyl, then I wouldn't expect any splitting on it. So it's not an isolated methyl alpha to a carbonyl. We don't have an aromatic ring. It could be benzylic, although even with benzylic, you wouldn't expect to have a visible coupling. You'll get the teeniest, maybe 0.5 hertz, but you won't see it except maybe in a cozy. Then we have a bunch of other protons, and as we inspect our way through them, we have some really nice patterns here. We have a QD, another QD, a triplet of doublets over here. We have a methyl singlet over here at about 1.3. So this is an isolated methyl. And then we've got a methyl doublet. And, as I said, I always just sort of calibrate my eye when I look at a spectrum. So methyl doublet invariably is going to be about 7 hertz. So these couplings here we'll see are about 10 hertz here, but you can kind of see they're bigger. Let's see what happened here. Did I have this thing duplicated? Okay, oh yeah. So that's what I did. I went through, I labeled my peaks A, B, C, D, E, F, G, H, I, J, K, L. If I had later discovered another peak hiding under one or a shoulder, and I realized, okay, I can parse that out into 2 peaks, I might have called something like G and G prime, but here every resonance really was quite well resolved. So I was able to get it all the way at once. Okay, here's our carbon NMR. And again, I've numbered our resonances. You can almost see the quats, right? They're the short ones. That 1, 2, 4, and 5, and 9 are pretty obviously quats. The depth is going to give that to us just fine. So we can get that from the depth. We don't tend to use depth 45 these days in the spec lab. Depth 45 gives all carbons with a hydrogen attached, whether methyl methylene or methine. But honestly, between the depth 135 and the depth 90 in the main spectrum, you can get everything you want. So I went through and I basically was able to pick out what the methyl groups are. We have 3 methyls, C12, C14, and C15. We have a couple of methylene groups, C11 and C13. And then we have a bunch of methynes in there, 3, 6, 7, 8, and 10 are methynes. All right, finally, I went through and I took the HMQC spectrum and I correlated my numbers and letters. And this on top here is going to be our Rosetta Stone 3A, 6B, 7C, 10D, 15E, 13F, 11G, 8H, 13I, 11J, 12K, and 14L. So that's going to be our working sort of Rosetta Stone for this problem. And that's where I've stopped on your handout 3, where I've stopped sort of the low level analysis that I thought wouldn't be as fun to take you through. Any questions at this point? All right, so I want to create a scorecard, and it's really useful at this point to have some sort of scorecard to keep track of things. So our C1 is a quat. It's at 186 ppm. I'm not going to do this for all of them, but I want to sort of notice at least some of the interesting shifts. C2 is a quat. It's at 178 ppm. It also seems to be a carbonyl. Maybe if I'm uncertain of that, I might put a question mark, but that seems to be a carbonyl. C3 is connected to HA. C4, C4 is a quat. C5 is a quat. C6 is connected to HB. All of these are down at 125 to 100, and I think it was 56 ppm. But all of these here are pretty clearly alkenes. And if I'm right that we have 2 alkenes, 2 carbonyls, then with our 7 degrees of unsaturation, that probably means we have three rings. All right, C7 is connected to HC. And C7 is really interesting, and HC is really interesting. So C7 is at 81 parts per million, and HC is at 4.8 parts per million. And that sure suggests that it's some sort of carbon and hydrogen next to an oxygen. So I'll annotate that because we don't get down to 81 parts per million easily. I mean, you need, even a nitrogen isn't going to bring you down there. We don't have a nitrogen. It's, not an alkene. And 4.8 is really interesting. Again, we don't get down to 4.8 parts per million easily. Let's see, C8, H comes on to our scorecard. Let's see, continuing, C9 is a quat. C10 is connected to HD. C11 is one of our methylenes. So C11 gets 2 diastereotopic protons. C11HG NHJ. That means we're going to get a lot of information off of these in the cozy if they're crossed with others. C12 is a methyl group, C12H3K. So that's that methyl doublet. C13HFHI. C14 H3L. So that's our isolated methyl. This is our methyl doublet. And finally, C15 is that oddball, C15H3E. So it's at 2.1 parts per million or 2.07 parts per million. And it's a doublet, 1.2 hertz is our J value on that. Make my E clearer here. Any questions or thoughts at this point in the analysis? All right, so at this point, I think I want to go through the cozy spectrum and start to try to build up our fragments here, build up any sort of chains we have. I'm going to go to handout number 2, and we're going to work that handout. All right, so these were the blank pages that I used for the initial analysis. Initially, I had people follow along with me on this, and then I just realized the lower level stuff is probably not worth scrawling wildly over. But I want to go and get us now to some of the higher level analysis. Okay, so I have this whole spectrum over here, and then I have an expansion that'll be a little bit easier to work on. So I'm just going to start with this part of the spectrum here. So we have 3A and 6B, 3A and 6B on our cozy. And of course, by now you should be quite familiar with your diagonal and probably not need to label it. And so we get 3A crossed with 6B. And I'm going to stop at this point for a moment, I think, and start to show you how I work things. So erase this board over here. So I usually start to jot notes as I work it. I might jot it on the spectrum, or maybe I'll have a separate piece of paper for my work. It's probably a little bit easier to have a separate piece. This is what I mean by fragments here. So, and the coupling constant was big. It was, you could see the doublet was quite big for those peaks there. So you could see that rather well. It was 9.9 hertz. So this could be a cis alkene, like so. And the only reason I'm maybe keeping things open here is it's conceivable we could have something like this. But no matter what, these two carbons certainly are alkene carbons. So anyway, so that's what's on my mind when I see that cross peak. All right, let's get into the rest of the cozy, and I'll go to the next page for the expansion. Didn't seem to appear properly. Let's try that again. All right, so on to our expansion. And again, very, very mechanically, very methodically, I'm going to label my way across the edge just to help keep track of things. So 7C, 10D, 15E, 13F, 11D, 8H, 13I, 11J, 12K, and 14L.
Sorry to interrupt. I think the first 11 should be G.
Oh, thank you. Thanks so much, Chris. And then I'll do the same thing over here. 7C, 10D, 15E, 13F. I'll just zoom in a little bit. 11G, 8H, 13I, 11J, 12H, and 14L. All right, now I'm going to work through our cross.
12K.
What? Oh,
It's 12K.
12K. Whoops, 12K. This is the problem when you can't read your own handwriting. Sometimes what I'll do to avoid problems is just write the letters out and then put the numbers on top. And honestly, that's probably what I should have done here. All right, let's go into our cross peaks here. So off of that, so remember that 15E is that allylic methyl that seems to be so interesting and giving so many interesting types of couplings to it. And we do see a cross peak off of 7C. So remember, 7C was that tremendously downfield methine that we thought must be next to an oxygen atom. The carbon's at 81, the hydrogen's at 4.7, 4.8 ppm. And so it's being shifted far downfield. So we see this peak of 7C with 15E. That's also the peak at 7C where I said, well, we see a small coupling in addition to the big coupling. It looks like a doublet, but there's shoulders on there. So that would certainly make sense for some sort of doublet of quartets with a small j. Then we see another cross peak off of that 7C peak with 8H. So we're kind of at this point off and running. And I think what I will do is do this one, and then we can build up our chain a little bit more here as we go. So we have C7H C. I think it's connected to an oxygen. We have that C8H peak over here. I always like to try to keep track of my valencies as I do things, just to help try to keep in mind where I need to be adding connectivity. So let's continue in our cozy over here. All right. So we get 10D crosses with 8H, and 10D crosses with 14L. And so again, I'm going to go to my little chart over here. And we've got 10D crossing with 8H and 10D crossing with 14L, C14H3L. And we have one more valence on 10D. All right, things get a little thick over here, but we're going to have lots and lots of redundancy built in. So one of the things that you'll want to do is realize that some of your peaks won't be very informative. So these nice strong ones over here, like this one. This one's 13 F cross 13I. It's fine. It doesn't really tell us anything new because those are the geminal couplings. There's a technique called cozy 45 that actually gives a different slant to the two peaks, and that can be kind of helpful because the geminal couplings typically slant one way. That's because the J values are typically negative, whereas the vicinal couplings, the 3-bond couplings, slant in the other way because they're typically positive. We have the same thing over here. We have this, what I'll often do is just abbreviate these 11X to mean it's 11 crossing with itself. It just saves a little bit of space. But then we get some things that are useful, like this over here is 13F cross 11J. And this may be a little harder to discern, but fortunately we get the same information. Actually, no, I take that back. This is 13F cross 8H. Then as we continue along here, this little cross peak over here, and we could work on the other side of the diagonal. This cross peak is 11G with 13I. This is another cross peak over here. Let's see, this one here is 8H with, let's see, why am I missing this? I think this is 8H with 13I. And I think we just have one left over here. It's J cross I, so it's 11J with 13I. 13I with 11J. So the good news on that, and that takes us pretty much through our cozy. The good news on that is there's a lot of redundancy built into this. So 8 is crossing with 13 in a couple of different ways. So we get C13, HF, HI, and that's linked to C11, HG, HJ. And again, I like to keep track of my valencies. So we have no open valencies here except one at the end. Questions or thoughts? All right. At this point, I find it useful to continue to keep track on a sort of a scorecard of what we have outstanding. So we have our C1 carbonyl, our C2 carbonyl, C4, which I think might be double bonded to C5. Although, as I said, there could be other ways to put this together. So I'm just sort of suspecting that C12, H3K, that isolated methyl, and C9 are quat. And I guess the other thing I think we still have is C15, C15 H3E, that methyl with that allylic type of coupling. Thoughts or questions at this point? All right, at this point, I want to turn our attention to the HMBC. And as I've said on quite a few occasions, HMBC can be like drinking from a fire hose. You have a lot of information there. But we're going to start with our carbonyls and our quats, our carbonyls and our isolated methyls. And honestly, that's usually enough to get us where we're going. So again, I'm going to number 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 are pretty close together. They're about a half a ppm apart. I wish I had given you an expansion on these, because a half a ppm, particularly if you do 512 increments in the F1 dimension. You can resolve with the digital resolution. At 256, it might be a little tough, but if you go to Ni equals 512, you can resolve down to a couple of tenths of a ppm. We've gone even as high on some of our problems, the final exam problems. We've gone even as high as 1024 when we've wanted to help people out with really close carbons. But I'll show you a trick here in just a moment that we're going to do, even though I didn't give you an expansion. All right, again, I'm going to continue. And I think to avoid stupid errors, I'm just going to go and first do my alphabet and then put my numbers on: 3A, 6B, 7C, 10D, 15E, 8F, 11G, 8H, I'm sorry, 13F, 8H, 13I, 11J, 12K, and 14L. And the next thing we're going to do is we're going to cross out the HMQC type of one bond couplings that we see that I affectionately refer to as vampire bites. So basically, peak number 14, carbon number 14, you can see we're getting J1CH coupling around this tall doublet that's 14L. So I'll cross those out. Similarly, on 12K, I'll cross those out. Let's see, what else do we see? We see one pair here around 10D. We see another pair around 7. We see another pair around 6. And I think there's one more pair here on the 15E methyl singlet. So we pick that up. Okay, so I cross those out. And then at that point, I'm ready to start analyzing my spectra. As I said, there's a lot of data here. I'm going to focus on a few isolated peaks that I want to try to place. So for example, we see that we cross 1 with 3A. It looks like we cross 1 with 6B. I'll put a little bit of a question mark there since that peak is really weak. We cross 1 with 15E. Now that's interesting. That's really, really telling at this point, because we know that we can't have that methyl group directly on the carbonyl, right? It wouldn't have any coupling if it were directly on the carbonyl. So that methyl group has to be on an alkene, but that methyl group has to be on an alkene that's not, that methyl group has to be, or that methyl group has to be on an alkene that's attached to the carbonyl. So that's, to me, that's really, really interesting. So, and we're getting 1 with 3A, 1 with 6B, 1 with that methyl group. And that's largely going to do a lot of placing here. So I want to show you what we're getting at this point. So at this point, we have our carbonyl number 1. And our carbonyl number 1 is crossing with 3, and it's crossing with 6. And so we have to have C3 or C6 connected and they're connected to each other, but I don't know which is which. So I'm not going to stress about this at this point. I'll just leave it as C3/6 is connected and C3/6 is also connected to HA/B. So basically, I'm going to deal with the uncertainty by just accepting it and moving on. And later on, in one of the other problems, you're going to have the same thing with the methyl group connected, and you're going to get cross peaks with an isolated methyl and two quats, carbon 6 and carbon 2. And you know the methyl group has to be directly attached to one of those quats and not directly attached to the other, but one over from the other. So just call each of those quats 2/6 and move on. Now that methyl group of C15HE, as I said, is really interesting because that methyl group can't be directly attached to the carbonyl. So that methyl group has to be attached to carbon 4 or 5. And so that's our methyl group C15HE. But if it were directly attached to the carbonyl, we wouldn't have any sort of coupling, any sort of proton-proton coupling. So it's got to be allylic. That makes sense in terms of the chemical shift, which means since it's not on either of these, if it were attached to this carbon here, it would be J coupling with a big J. So it's got to be placed over here. Okay, let's continue here. All right, so I'll continue with this idea of focusing on isolated peaks like the carbonyls. So let's focus on carbon number 2. Carbon 2 is crossing with 10D, and carbon 2 is crossing with 14L. So that again is really, really telling because that places our carbonyl number 2. So here's carbonyl number 2, right? It can't be directly attached to 14L. We're picking up our J2 and J3CH coupling. To use James's favorite expression, the absence of evidence isn't evidence of absence, particularly in the case of a methine where you have dihedral angles, but a methyl group, it probably would be evidence of absence. So I'm not particularly bent out of shape by not getting a cross peak with HH, but that places this here. We had already been thinking about a lactone, a gamma lactone, and so I might as well close up our lactone. If you don't want to do this at this point, we're going to use up all of our valencies in just a moment. So let me come to the last piece of information that I want to get out of here. Now, and so I'm going to come over at this point. I'm going to come over at this point to our isolated methyl. I'll come to 12K. And 12K really ends up being a nice linchpin. This is a common feature when you have isolated methyls. So we get 12K with 11. We get 12K, and you might say, okay, well, I'm not really sure if it's crossing with 9 and 10, and I didn't give you an expansion, but we filled out all of our valencies on carbon 10, and it has to be on a quat. This is the only quat we're going to cross with, because we continue down here, and we get 12K with 4, and 12K with 3. And so that, and it's not an allylic methyl. It's not a methyl on a double bond. That would put it at about 1.7 ppm. So that's really our linchpin. This is the last I'm going to show with the HMBC spectrum. So I wanted to point out one thing that some people have pointed out to me.
James, may I interrupt you really briefly? Yeah. I think you meant to write 12K with 9 as the cross peak, because you just mentioned how.
Thank you, James. Yes. That's 12K with 9. That's 12K with the quad. All right, I wanted to point this out for anyone who did analyze the hell out of the spectrum. We do see a cross peak of 3A with 7. This is a J4CH that's coming up. This is a long-range coupling that's coming up with basically some type of W coupling that's coming up. For anyone who saw this, that may be surprising. All right, I want to finish up at this point, and if I can't finish up, I will finish up in discussion here. Okay, so that's the linchpin. So C12H3K crosses with carbon 9. It crosses with carbon 3. It crosses with carbon number 4. And it crosses with carbon number 11. And that's pretty much the linchpin that allows us to put this whole thing together. Because at this point, first of all, now we've assigned our carbons. This is number 4. This is number 5. It's crossed with, I think I said 3. So this is number 3. And its proton is A. This is number 6. Its proton is B. And we have 2 valencies. We put our structure together over here. I'm going to, at this point, redraw the structure neatly, make my 6-membered rings look like 6-membered rings, and so on and so forth. And I want to take us to the last bit, the stereochemistry and conformation of the molecule. So we start C14H3L. That comes into C10HD. That comes into C8HH. That comes into our C2 carbonyl. That comes to our oxygen. That comes to our C7HC, pardon me. This comes to our C13HFHI. That comes to our C11HG, That comes to our C9, that comes to our C4, which is double bonded to C5. And that comes to C3HA. We have C12HK coming off of here, C6HB, C1 carbonyl, C15 H3E. And I think rather than rush through the stereochemistry and conformation, because we're already 5 minutes over, I'm going to pick up on that at the start of discussion section So I will take, rather than rushing through the stereochemistry, we'll just pick up on that in the first 5 minutes of the discussion section. Are there any questions about the connectivity and other aspects of the molecular structure?
James, if
Yeah.
I remember correctly, and we have time to discuss it, there is one strange cozy cross peak between the methyl that's the small allylic doublet. Is that correct? We discussed this in jam session last night. I forget exactly which correlation it is that's under.
Right, that's the, okay, yes, that's the C7H15E. So that's a coupling from here over to H. That's C7, okay, yeah. So this coupling is right from Silverstein. This is what I generally refer to as homoallylic coupling. It's a long-range coupling. So just as we will have a CH over here, and our coupling, if we see it, is usually 0 to 3 hertz, this is what we call allylic coupling. We may, and again, this is right out of Silverstein, we may get coupling from an allylic to an allylic. So this is a J4CH. We may get coupling all the way from one side to the other. And again, we're talking 0 to 3 hertz would be typical, with 3 being on the extreme side. This is a J5 HH. I've got CH on the brain. That's an HH coupling here. So that's a J5HH. And we've seen the same thing in the homework in propargyl systems, where we've seen this, and this is also a J4CH. And I think we have even seen this, a J5HH. Why do I keep writing CH? HH. So yes, so indeed we do have a long range coupling there. And I'll point out that these do depend on dihedral angles. But the nice thing, and why it's particularly prevalent with a methyl group, is a methyl group is always going to have some good dihedral angles that can lead to overlap of the orbitals. So yes, so that's the last feature here that's sort of an oddball on this. All right, I want to let you go. I know we've run long, and I will pick up on this where we left off at 5 o'clock. Well, I wanted to pick up where we left off this morning to finish up with the with this homework problem and the structure determination. So I think where we left off on the problem, we had elucidated the aliphatic portion of the molecule primarily by COSY. We used HMBC to stitch the pieces together. Most notably, we were able to stitch in the carbonyls, the allylic methyl group, and very importantly, that isolated aliphatic methyl group that served as a linchpin. And I made the point that when you have a methyl group attached, that's isolated, attached to a quat carbon, you're going to pick up cross peaks not only with that quat carbon, but with each of the carbons to which that quat carbon is connected. And that can be a really valuable way of stitching these structures together. So at this point, we have all the connectivity of the molecule, and we have some stereochemistry to establish on this. Most notably, we have the stereochemistry of the ring junction here, the methyl group over here, and the methyl group over here. So basically, we need to figure out what the relative orientation of these substituents is. We have a 6-membered ring here that probably will end up being a chair-like cyclohexane, although it could be in a boat conformation. We have a 5-membered ring. And so in this particular problem, I've provided 1D NOE spectra rather than 2D NOE spectra. And so I wanted to go through the data. All right, so I'm going to share my screen from the 1D NOE spectra. And so the first irradiation I want to emphasize is over here, and it's a little hard to tell what we're hitting, specifically whether we're hitting the methyl doublet, the C14H3L, or the 14K or the 12K methyl. We can see over here, so we're hitting primarily L. So this is just, I had plotted all of these on one page, but you can't see the peak that's being irradiated, which is right over here. So I've taken us here. So we're primarily hitting but you notice we don't get complete selectivity. In general, in the NMR and in a 1D NOE spectrum, it's very hard to hit one peak selectively when it's closer than when it's within about a tenth of a ppm of another group. Often I end up going for the isolated peaks. We're going to see there's enough information here, enough redundant information that we don't have to worry here. But primarily we've hit 14L over here, and we see that we get a big enhancement of 10D, and we get some little enhancement of 13F, and we get some little enhancement of 8H. And then over here, I'll draw this all out in a second. Over here, we hit 10D. And we get a little bit of enhancement of 13I. Now, you may wonder what's going on over here. And you'll notice we have up, down. I didn't slap an integral on this one. This is 8H over here. And this is pretty typical of what you'll see when you have J coupling. So there may be a little bit of an NOE to it, but primarily the fact that we have some going down and some going up is a product of there being J coupling. Any net, remember, will have a negative area for this part that's going down and a positive area for the part that's going up. So I'm not nearly as interested in that. Plus, it's kind of a trivial NOE because it's a 1-2 NOE. And then notably, we get enhancement of 7C. And then what I think is nice and telling, because it's useful to have multiple sort of complementary approaches here, is we irradiate 7C over here, and we get 10D, and we get 13I, we get a notable NOE to, and also to 12K. So I want to diagram this out at this point so that we can get a better view of what's going on. So we irradiate 14L, and we get an NOE to 8H, and we get an NOE to 13F. Then in the next experiment, we irradiate 10D, and we get an NOE to, pardon my chair there, we get an NOE to 7C, and we get an NOE to 13I. And I like these non-adjacent NOEs because adjacent NOEs aren't very interesting. Adjacent NOEs generally, you know, even if two protons are trans to each other, you may well get an NOE. But particularly like on a 5-membered ring, this type of NOE across the ring really is pretty good indication these protons are cis to each other. And then the last experiment, we irradiate 7C. So we irradiate 7C, and now we see an NOE back to 10D. We see an NOE to 13I, and we see an NOE to 12K. And that's really interesting because these NOEs, I would have loved to have hit 12K on its own. And if we had an OSI, maybe we could have. It was a little crowded for 1D and for selectivity. But we can tell, basically, we've got this locus of NOE on one face of the ring here. And so if I start to draw that ring, I think you're going to see how this all comes together. So I can imagine if I start with a chair cyclohexane, and let's say I put my C12H3K in the axial position. And then if I have over here, I have my HI over here. And if here, and I guess if I want to be a good person, I'll break that little line in back. I have my HC. That can explain this locus of NOEs across here. Then at this point, we can draw in our ring with the double bonds. And I can draw on my methyl group. This is our C15H3E methyl group. And then usually the way I try to draw a cyclopentane ring that can be pretty good for an envelope is you draw it just like a cyclohexane ring, but you close it off at a 5-membered ring. So imagine if I had drawn a bond right over here, that would be a pretty good facsimile of a cyclopentane ring in an equatorial conformation or in an envelope conformation. And so I can finish my drawing like this. And now that gives us a good excuse to draw HD pointing up, kind of continuing that axial thing. That puts this methyl group into an equatorial position, C14H3L. I can continue with my drawing over here. HF, right? This is carbon 8, so I can continue with my drawing over here. HH, maybe just to help orient, I'll write a little 10 here, a little 8 here, and a little 13 over here, and a little 7 over there. I think that helps us orient rather nicely. So I think with that said, I've pretty much completed my structure. You could imagine additional experiments that we might want to do. I think the next thing I would do if I wanted to was make a model in PyMol, clean up the structure, check out for short distances. Now, all of these distances here are going to be about 2.5 angstroms. So these are going to be screaming NOEs. Ditto for this distance here. Although HF and HL don't look that close, if you actually make a model or you're good with seeing things in 3 dimensions from my drawing, they're actually quite close to each other. So that pretty much sets our knowledge now of the stereocenters in this molecule. So questions or thoughts at this point? Is this hard for people to see from this distance? It looks like people are copying. I'm gonna go ahead and pin that video, and I'm gonna do a quick screenshot of this. I'll take myself out here, and I'm going to drop that in the chat box so I can close this screen and we can move on here.